Alrighty, so op amps are very common electrical components that we have to deal with in a lot of different circuits, various applications. First off, because they're very cheap to manufacture, and second off, because they're very useful. However, they are fairly complicated. You see, we have lots of transistors and resistors and capacitors in here, and we really don't want to deal with all that. So we just have a simple schematic that we use with 5 inputs, and we just imagine all that stuff in there is happening, but we don't worry about it. So the only things that we have to worry about are the inputs and the outputs to this little black box that we have, or black triangle that we have here. The first two being VP and VN. These are our non-inverting and inverting inputs, or the positive and the negative inputs. These are the things that we will be manipulating, amplifying, summing, differentiating, all sorts of things. These are the signals that we will be operating on for our op amp. The next two are VC plus and VC minus. These are our power supplies for the op amp. Our supply terminals. These are what give the op amp the power it needs to manipulate our inputs here. And finally, we have our output, V out. This is the output of the op amp. Whenever it's done manipulating the inputs, it goes to the output terminal. Alrighty, so there are a couple of rules that we have to follow when we're dealing with this simplified model of an op amp. First off, we know that VP will be equal to VN. So the voltage at this node and the voltage at this node will always be the same when we're analyzing this within a circuit. Also, we know that our output has to be between our input or our positive supply and our negative supply. So a better way of saying that is VC minus is less than or equal to V out is less than or equal to VC plus. So this is just saying that our negative supply and our positive supply define the range of outputs that we can output from our op amp. So if we have like 5 volts up here, we know that V out can never be greater than 5 volts. And same for our negative. If we had -5, V out would not be able to be less than -5 volts. And then the final rule that is useful has to do with the currents at our input terminals. That'll be IP and IN. Due to the nature of the op amp, we know that IP is equal to -IN, but really they're both just equal to 0. So remember this right here, IP and IN are both equal to 0 in the ideal model of an op amp. So yeah, let's go ahead and start solving some circuits with this. Alrighty, so in this first circuit, we actually have 2 op amps, but don't be scared. One of the best properties about an op amp is its buffering property. So what that means is we can essentially analyze them one at a time, because the op amp has the ability to supply however much current it needs to keep V out constant. So no matter what's going on over here, the output of our op amp will stay the same. Within reason, at least. Okay, so we're going to look at this node right here, because the first thing we're going to try and find is our V out 1 over Vn. So that's the first stage gain of just this right here. So we're going to apply KCL at this node here. So we have a current going out there, current going out there, current going out there. But this is our IN current. So we know that it's equal to 0, so we can just ignore it. So we only have two currents here. We have our this is our VN node. So we have our VN minus V out 1 over 10K, and our Vn minus Vn over 5K, and that's equal to 0. But if we remember from one of the other rules of the op-amp, we know that Vn has to be equal to Vp. And as we can see here, Vp is connected to ground, meaning it's 0 volts. So for this equation here, we can plug in 0 for Vn. So what we get is negative V out 1 over 10K minus Vn over 5K is equal to 0. And this is good. We have one equation, two variables, and we're trying to solve for the ratio between them. So this is all we need here. We're just going to do some algebra. We get bringing over Vn to the other side. So our gain for the first part here is negative 2. Again, gain is unitless since we're dividing resistance by resistance, or voltage by voltage. It just cancels out. So now for our second segment, V out 1 over V out 2, V out 2 over V out 1. We're just going to apply this same principle, but we can probably skip a few steps now because we can see there's the same thing happening here. At this node, Vn is equal to 0 volts, and we only have two currents going out. The one going to our output and the one going to V out 1. So we're going to go ahead and write out Vn minus V out 1 over 4K plus Vn minus V out 2 over 16K equals to 0. So applying the same steps as before, so we know our second stage gain is negative 4. So when we want to find the overall gain from our input all the way over here to our output all the way over here, we already have everything we need. So to find V out 2 over Vn, that's just the same thing as our first stage gain, V out 1 over Vn, times our second stage gain, V out 2 over V out 1. So you can see these cancel right here, and we end up with the same thing. So if we plug in our numbers, that would be negative 2, negative 4. So our overall gain is 8. Alrighty, let's go on to the next one. Okay, so for this circuit, we have an op-amp with a variable gain that is controlled by the resistance of this potentiometer, Rp, here. So we need to find a function for V out in terms of Rp. So as we vary Rp, we want to find what our V out would be at any given point. And if you'll notice, it needs to be a piecewise function, because from before we have our power inputs here. So we know that V out has to be in between these two power voltages, or power inputs, power supplies here. So our graph will end up looking something like this. We're in the middle here. This is called our linear region. And on the edges, it's known as saturation. So linear is the normal region. That's where all our other op-amp rules apply. But on the saturation region, that's the place where the op-amp wants to output a higher voltage, but it's limited to its power supplies. So it's just going to output however much it can. In this case, -5 or 5 volts. So let's go ahead and work this out. So first off, it'd be good to just analyze this normally and find an equation for V out in terms of RP. So if we're looking for extraordinary nodes, it looks like this is our only option right here. We'll call, this is Vn actually. As you can see, it's connected directly to the negative input. So let's go ahead and write an equation for all the currents exiting Vn. We'd think it'd be 3, but if we remember one of the op-amp rules, no current enters our terminals, our input terminals. Clarify, our input terminals. So current can enter here, and current can exit the output or enter the output. But no current can enter or exit our input terminals. So we only have 2 currents to worry about here. It would be Vn minus V out over Rp, and then plus Vn minus 0, since we're going to ground, over 5K. All that's equal to 0. So we have one equation here. We want Rp in terms of V out. We need to get rid of V in somehow. So we look at this. We know that Vn has to be equal to Vp, if we remember. Our Vn is here, and our Vp is here. So what is the voltage of Vp right here? Well, since we have no current going into this terminal right here, there's no current going through this resistor. And if there's no current going through the resistor, that means there's no voltage drop. So that means this 1 volt stays constant all the way to Vp. So Vp is equal to 1 volt. And Vp equal to Vn, we know Vn is equal to 1 volt. So let's plug that in real quick. We get 1 minus V out over Rp plus 1 over 5K equals 0. So now we just play the simplification game. So we want V out on the left side, Rp on the right side. So let's go ahead and get that fraction on the right side. That'd be negative. And then we can multiply by Rp. Then we can get rid of the 1. And then we can just multiply everything by -1. So this is our final equation for V out in terms of Rp. But this is not accounting for our power limits up here. So we need to find the limits, the bounds of this equation, and then turn it into a piecewise function. So let's go ahead and do that. We know the lowest RP can go is 0. So let's see if that's a limit right here. If we have 0 over 5k plus 1, that's just 1. And 1 is within our bounds. So we know that's good right there. So we don't have a minimum resistance. 0 is a valid resistance. So now let's see if there's a maximum. So we know V out, our max V out is 5 volts. And if we set that equal to our equation here, we can solve for the resistance at which V out reaches that maximum of 5 volts. So we subtract 1, multiply by 5k, and that is our upper limit right there. So RP can go from 0 ohms to 20k ohms while V out is still in the linear region. So let's go ahead and write a piecewise function that represents that. So V out of RP is equal to, we know RP over 5k plus 1. We know this is valid from 0 to our maximum here. So for 0 less than or equal to RP less than or equal to 20k. Get this out of the way. And then whenever it reaches this limit, this upper limit where it's 5 volts, we can't output any higher than that. So it'll just be 5 for that RP greater than 20k. And that's our final function right there. So if we were to graph this, V out as a function of RP, we would be increasing V out by increasing our RP. It's a positive relationship. But then once we reach that point where RP is 20k and V out is 5 volts, that's where we flatten out and it just becomes 5 volts. So again, this is our linear region, and this is our saturation. Alrighty, that's all.